Good day for everybody. Thank you very much indeed to the session organizing for this invitation and you for coming here. Bernoulli and Gegenbauer polynomials are among classical families of algebraic polynomials whose history goes back centuries. Each one of these polynomials, as well as their natural generalization, has shown their useful in several disciplines. I'm going to talk about a mixed type of special polynomials obtained from generalized Bernoulli polynomial and Gegenbauer polynomial by means the product of their generated function. As you can see in the expression 1 and 2. So, the outline of my talk as follows. First, a short introduction showing some basic facts about the generalized Bernoulli polynomial and Gegenbauer polynomial. Next, I will introduce the generalized mixed type Bernoulli-Gegenbauer polynomials and their properties. And finally, I will comment some reference related to this subject. Okay. The generalized Bernoulli polynomial can be defined by means the expression 3, like the coefficient in this power series. These polynomials are in variable x, degree n, and order alpha. This polynomial generalize the classical Bernoulli polynomial in the sense that when we take alpha equal to 1, we recover the classical Bernoulli polynomial. The generalized Bernoulli polynomial also are associated with certain numbers. This number appear when we take x equal to 0. Are called generalized Bernoulli number of order alpha. Again, when we take order equal to 1 variable equal to 0, we recover the classical Bernoulli numbers. Also, the generalized Bernoulli polynomial was studied by Professor Milne Thompson in 1933. More recently, a brief study on this family was done in the book of Professor Rivastava and Choi. In addition, you can find another information of sequences of numbers associated with this polynomial in the website of the online encyclopedia of integer sequences or Wolfram Matchboard. The properties 1, 2, and 3 are a straightforward consequence of the definition of generalized Bernoulli polynomials. Will the property 4 and 5 was shown by Professor Rivastava and Todorov in 1988. These properties are a little different because property, property 4 express the generalized Bernoulli polynomial in terms of the Gaussian hypergeometric function to f1, and then taking x equal to 0, property 5 give a representation for generalized Bernoulli numbers. As you know, the classical Bernoulli polynomial admits different representation. Between this representation is the inversion formula in this slide, property set. Inversion formula tell us that the first n plus 1 classical Bernoulli polynomial forms a basis of Pn. Pn in this talk denotes the space of polynomials of degree less than or equal to n. Okay. A similar property to the inversion formula in the classical setting holds for sequences of generalized Bernoulli polynomial when the order of this polynomial is taking a natural number. This is the content of the property 7. So, if we take a fixed natural number m, take any n greater than 0, the set of the polynomial bm0 is also a basis of the space of the algebraic polynomial of degree n. In the case of the Gegenbauer polynomials, is well known that if we consider a parameter alpha greater than -1/2 and denote Cn hat alpha, the sequence of Gegenbauer polynomial, as you know, orthogonal on the interval, compact interval -1, 1 with respect to the Gegenbauer measure, excited by the rest condition in the slave. We know orthogonality relation. Our normalization doesn't not allow alpha to be zero or negative integer. Nevertheless, the following limit exists for x in the interval minus 1, 1, so that we can define the Gegenbauer polynomial of parameters alpha equal to 0 in terms of the Chebyshev polynomial of first kind. Now, if we denote the monic Gegenbauer orthogonal polynomial of degree n by this expression, we know Gegenbauer polynomial contain the Legendre and Chebyshev polynomial as a special case. Gegenbauer polynomials are closely connected with axially symmetric potential in n dimension, like application. And this polynomial inherit almost the formulas now in the classical theory of Legendre polynomials. Good. Between the more important properties of Gegenbauer polynomials, we know the 3-10 relation, 3-10 recurrent relation, sorry. The explicit expression for they know, for instance, differential relation given by the Rodriguez formula. Remember that the 3-10 recurrence relation and Rodriguez formula represent a equivalent definition of the Gegenbauer polynomial with respect to the definition via orthogonality relation, right? Good. Another properties of the Gegenbauer polynomials are the structure relation or the well-known Hahn condition. Remember, the Hahn condition tells us that the derivative of Gegenbauer polynomial is another Gegenbauer polynomial of the parameter increase in one and degree decrease in 1 unit. In our case, in order to deal with definition by generating function and power series, we are interested in the definition to the monic Bernoulli-Gegenbauer orthogonal polynomial by mean generating function too. So the representation or definition considered by in this slide is concerned to definition given by generating function in each case. Okay. Now, this representation is important because we are interested to multiply the generative function associated with this polynomial times the generative function associated with generalized Bernoulli polynomials. Now, with this information in mind, we can define the generalized mixed-type Bernoulli-Gegenbauer polynomial, in short, GBG polynomial, multiplying the corresponding generative function and considering the power series associated to the new generative function. Again, we have a GBG number taking x equal to 0, and when alpha, the order is equal to 0 and x is equal to 0, we use in this case the second representation of the GBG polynomials. Good. It's not difficult to prove with this definition that the sequence of GBG polynomials of order alpha satisfies certain explicit formulas like 15 and 16 formula. Notice that the 15 formula, the order alpha is different to 0. It's different to 0. Will in the 16 formula, the order alpha is equal to 0. Now, for example, using in a convenient way some of the previous relation, it's not difficult to check to the first 4 GBG polynomials are given by the expression in the slide. Okay. Notice that in a similar way to the case of Bernoulli generalized Bernoulli polynomial, in this case also appear another family of polynomials when we consider the parameter alpha. Okay. In other words, the coefficient in that polynomial represent another family of polynomial, this time in variable alpha. Okay. And using the expression 56, remember the expression 56 is the definition of the GBG polynomials when alpha is equal to 0, and the properties of the Bernoulli-Gegenbauer orthogonal polynomial. We can obtain the explicit formula or the explicit expression for the GBG numbers when the order alpha is equal to 0. It is worth pointing out that the generative function appearing in the expression 1, let me show. This generative function can be expressed as this product, where G alpha is this function and G is the another function. Hence, the polynomials, the GBG polynomials, are not generalized Apple polynomials. Also, in contrast to the generalized Bernoulli polynomial and Gegenbauer polynomial, the GBG polynomial neither satisfies a Hahn condition nor an Apple condition. The previous remark 1 and 2 can be checked using the following lemma. The statement of this lemma is the following: for alpha belong to the open interval minus 1 over 2 infinity minus 0. The sequences of GBG polynomials of order alpha has the following property. We can take the polynomial of degree n plus 1 and its derivative, and result that in this derivative correspond to this expression where the polynomial 8n is given by this formula. So this expression for the derivative of the GBG polynomial implies that this family of polynomial cannot be a sequence of apple or a sequence of generalized apple polynomials. Another interesting property of this polynomial is associated to relation of with respect to or orthogonality. It's clear that when we consider some relation associated with the orthogonality, we need the Gegenbauer polynomial. Well, for our sequence of GBG polynomial order alpha, when alpha different of 0, the relation between the inner product associated to the Gegenbauer polynomial and this polynomial is given by this formula. In the matrix framework, in the matrix context, we can use the expression 15 in order to obtain a matrix form of the GBG polynomial of degree R for R from 2 to n. And this expression is given by mean. It's given by mean the product of two matrices. The first matrix contains the information related to Gegenbauer polynomial, and the second matrix is the transpose of the vector of the first n+1 generalized Bernoulli polynomials. This representation is important because this representation allows us to express the vector corresponding to the n+1 GBG polynomials in terms of or in the matrix context. So the vector, the matrix vector containing the information about the explicit representation of the GBG polynomial can be expressed by mean this product of matrix where the matrix C alpha X is given by matrix to order n+1 the matrix with order n+1, and this matrix Cn has a special property. This matrix is triangular matrix with the property that diagonal diagonal correspond to the Gegenbauer polynomial, the monic Gegenbauer polynomial of the Greek one. Therefore, 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 this lower triangular matrix has a determinant, and its determinant is equal to 1. So, the matrix C alpha X is a singular matrix for each X in R. Each X a real number. So this matrix expression for the vector contain the information of the GBG polynomials allows to determine a way to find the explicit representation in the canonical basis of polynomials of the GBG polynomials using a inverse process of multiplication of matrices. So we can find inversion matrix formula. And the sample 3, in the sample 3, we consider n equal to 3, alpha equal to 1, using the previous information and standard computation allows to obtain that matricial expression for the classical Bernoulli polynomial, where the GBG polynomials of order alpha equal to 1 is given by this matrix. Since we know the inverse of this matrix, then we can recover the explicit expression for the first Bernoulli polynomials, for the first classical Bernoulli polynomials. In the example 4, this inversion formula for GBG polynomials can be given making the substitution of equal to 1 Oh, sorry, no. In this example, um, we show the matrix inversion formula for the GBG polynomial when the parameter alpha, order alpha, is equal to 1. When we take alpha equal to 1 into Z, remember Z, remember Z. Z is the property tree which give explicit formula for the Bernoulli generalized Bernoulli polynomial in terms of the generalized Bernoulli numbers. So, using this expression, we obtain that the matrix Bx can be expressed as this product of matrices, where M is given by a matrix, lower triangular matrix, where the diagonal of this M matrix is precisely the Bernoulli numbers, Bernoulli's number B0, and product of the Bernoulli number is 0. And the matrix Tx is the transpose of the canonical basis. So, again, it's clear that the determinant of M is equal to 1. So, M is a non-singular matrix, and making the substitution alpha equal to 1 in 20, remember the expression 20 is given by a matricial expression, a matrix expression for the matrix contains the information of the BG polynomial. Okay. Sorry. We obtain a matrix representation for the GBG polynomials, or matrix representation for the matrix contain the information of BG polynomials. So using the property of the important property of M is a not singular matrix, it follows that the matrix with the information about the canonical basis can be expressed in terms of this product. That is, we have found a matrix inversion formula for involving the GBG polynomials. On the account of 9, remember of 9, remember of 9, 9 is, the equation 9 is the inversion formula for classical Bernoulli polynomials. Form of 9. We obtain the following matrix equation where Q, the matrix Q is given by this expression, and consequently we can deduce a matrix representation formula for the matrix containing the information of the GBG polynomials as follows. Also, this matrix identity allows to conclude the set of the GBG polynomials is a basis for the space Pn. In view of 10, that means in view of the inversion formula for the generalized Bernoulli polynomial, it's possible to deduce a matrix inversion formula for these polynomials too. In this case, the identity takes this form, where Qm is an n plus 1 lower triangular non-singular matrix for the order n and natural number fixed. Okay. And then applying theorem 1 or equivalent, making the substitution alpha equal to m in the previous relation, we obtain another representation, another inversion matrix formula, matrix inversion formula for this case. Finally, I want to mention some reference associated with the theme, with the subject, sorry. Some reference associated with this subject. First, I only want to note the reference in green. The reference in green represents the main reference in order to the information of the task. The another reference, the reference in black, represents a good bibliography about a special function and orthogonal polynomials. A special function like Bernoulli polynomial, generalized polynomial, etc. Well, I hope you have enjoyed this talk. And thank you very much for your attention.